Hello, everybody. So I hope you have been learning a lot about differential calculus, learning how to differentiate all sorts of functions, whether it's a product or a quotient or x to the nth power or polynomials, whatever. Okay, but still we have a lot of functions we don't know how to differentiate. All right, so we are going to, in this section, section 3.5, talk about how to differentiate trigonometric functions. We have 6 basic trig functions, and we are going to learn how to differentiate them. A little bit of a historical background. Back decades ago when I took calculus, most of the calculus books are what is today called late transcendental type of teaching, which basically means things like trigonometric functions and log functions and exponential functions are not introduced in terms of their derivatives until like the second semester or later. And so, but in recent years, most books, most teachers, most schools have shifted to what is called the early transcendental model, which I believe is good. So in section 3.5, in this video, we are going to learn, and you will probably enjoy this. And in fact, if you stand back, you will be fascinated by the implications of the trigonometric functions. When you take the derivative of sine, what do you get? How about cosine? How about tangent? All these things are going to be related to each other in some fascinating way. Okay, so don't miss that wonderful connection between or among the 6 trig functions. Okay, so let's get started. Section 3.5. Derivatives of trigonometric functions. So we'll go right into differentiating things like sine and cosine. Ready for it? Okay. Now we had, remember I said back in chapter 2, we said there are 2 important functions, limits, 2 important limits that we will need to know. And those are these. Okay, so limit as x approaches 0 of sine x over x turns out to be 1. You see back in chapter 2, we proved it we first found the answer by XY chart. Okay, and later using the squeeze theorem, or what I call the sandwich theorem, in my opinion, a better name, we found that the limit was equal to 1. Okay, we also found that when you take 1 minus cosine of x divided by x, if you take the limit of this function as x approaches 0, it's going to give you 0. Okay, and by the way, if you switch these, you get the negative of this limit, which is -0, which is 0. Okay, so that doesn't matter if you see 1 minus cosine x or cosine x minus 1. All right, so with that, let's get started in finding the derivative of the sine function. I hope this symbol does not bother you anymore. d dx of sine of x, which means the derivative of sine of x. If you want to, you can still write this. You know that it does make sense. I know what you mean when you write this, and it is an acceptable way to designate or to describe the derivative of the sine function. But this is a more acceptable way to denote the derivative of sine. All right, so that is equal to, now we have nothing to go by, so we have to go back to the definition. All right, so this will be the sine of x plus h minus the sine of x divided by h. Okay, by the way, I remember the first time, this is just really, by the way, it should be on the footnote, but I remember the very first time my college instructor, which I still remember, Professor Taylor, showed me how to do this. And I was really fascinated with the answer because I was expecting, the derivative to be some really, really complicated function. And the answer was like, my goodness, this is unbelievably elegant. All right, so keep this in mind. All right, so what can you do next? Not much. You can't factor anything, right? But we do have a formula for the sine of a plus b, or alpha plus beta. That's sine of, okay, so sine of x plus h is sine of x cosine of h plus cosine of x sine of h, and then of course you have minus sine of x at the end, right? All right, so far this is what you get. The denominator is h, and the only thing we can do at this point is, you see sine of x twice. Okay, they don't cancel. but you can factor it from the first and the third the term. So cosine of h, cosine of h minus 1 plus cosine x sine of h. Rather long expression, but we have seen longer. All right, and at this point, again, we may get stuck. Okay, but think about this: sine of x. This expression is h free. In other words, there's no h in it. So you may want to just take this out. Okay, it's sine of x times the limit as h approaches 0. I'm hoping this limit exists. And in fact, we know it does, because that's exactly what I just described right here. Well, not exactly, it's the opposite, okay? But yeah, I mean, I did mention it, right? So the limit of cosine of x minus 1 over x is equal to the negative of this value, but that's still 0, okay? So I know this limit is going to be 0, and that's nice. All right, the second term here, cosine of x is still here. That's free of any h, so we can take it out. And now the rest is the limit as h approaches 0 of what's left. That's that, sine of h. And of course, you still have the denominator. We split one fraction into two fractions, so the denominator is repeated. Okay, hopefully you recognize this thing and that thing, okay? This limit is 0. This limit is 1. You see the beautiful answer here? This part just becomes 0. This is cosine. All right, I am here to say that the derivative of the sine function is simply the cosine function. Wow, right? You should be saying that. I can hear you, but you should be. All right, let's go to the next one, the derivative of the cosine function. Okay, again, you can write this as cosine of x with a prime. I will know what you're talking about. Now that we know how to do this kind of thing, I think you can probably do this on your own. Maybe you should pause this video and try to work this out yourself. Cosine of x plus h minus cosine of x all over h. Okay, what's the next step? Probably use the sum for the angle sum formula for the cosine, right? So that would be cosine of x, cosine of h, minus sine of x, sine of h, and then of course you have the cosine of x at the end. All right, and so what can you do after that? I can factor out. Maybe this will work, maybe it doesn't work. Cosine of x appears twice, they don't cancel. So once you take out cosine of x, you have cosine of h minus 1 all over h minus sine of x, sine of h. Remember I said earlier that many students struggle in Calculus 1 because they struggled with trigonometry. And so you really do need to review your trigonometric identities, trigonometric equations, definitions, and how to algebraically manipulate these things, okay? Now, again, cosine x is free of h, so you can factor it out in front of the limit notation. And then you have cosine h minus 1 over h. This should look familiar. And then minus sine of x is, again, does not involve any h, so you can take it in front of the limit as h approaches 0 notation. And what you have left is sine of h over h. Okay, so that's this over that. Okay, no problem here. You have seen this, that's 0. This, that limit is equal to 1. So this becomes 0 minus sine of x times 1, which is, of course, 0 minus sine of, it's negative sine of x. Too bad you have that negative sign. You know, if it didn't have it, it's even more beautiful. But here I have just proved that the derivative of our cosine function is negative sine function. All right, so they are related to each other. The derivative of sine is cosine. The derivative of cosine is negative sine. as I said, that negative is a little unfortunate thing, but not terribly bad. Okay, so well, let's. I mean, is this really right? Is this hard to believe? I think it's hard to believe. I think you should be shocked. Like it works out so nicely, right? Because after all, I mean, what's sine? I mean, sine was an opposite over hypotenuse, right? The derivative of that happens to be the adjacent over hypotenuse. It just doesn't seem to make sense. It shouldn't be this easy. But again, the world of mathematics is full of surprises, just like this, where you just can't believe this. Like it's like there is this order, the consistency, the elegance in the world, the abstract world of mathematics. Okay, what I was going to say is you have this sine function, which is going to be like this. Now, this is pi, which is like a little over 3, and this is 1, right? So this is, I'm trying to draw this to scale, like 1, 2, 3. Your pi is, of course, a little bigger than 3, and this is 6, and 2 pi is 6.28 something, and this is -1 here. And so the real function, sine function, actually looks sort of like this, right? All right, so this is the sine function. All right, what's the derivative at pi over 2? Oh, maybe I should write. Here's pi over 2, just around 1.57 something, right? And then this point is 0. Okay, what's the derivative of sine function at pi over 2? Now, from our experience, we know this is the highest point where the derivative is 0. Is that right? Okay, so all right, so f of x is sine of x. The derivative is a cosine of x, and that is going to give you the slope, right? The slope of this green segment I just placed on top of pi over 2 should be the derivative evaluated at pi over 2. That's cosine of pi over 2. Now, what is cosine of pi over 2 or cosine of 90 degrees? Yes, it is 0. And it is consistent with what you see here, what you observe here, because it's hitting its highest point. The tangent should be horizontal. Okay, how about at pi? At pi, the derivative, the slope seems to be negative, right? And I ask you, what is cosine of pi? It's -1. Okay, so the slope of the sine function right at this point, pi, comma 0, turns out to be exactly -1. You didn't know that, did you? The rate of change of the sine function at pi is exactly -1. The tangent line has the slope of -1. And how about this point, 0? The slope is certainly positive. And how high or how big is the slope? The answer, it's cosine of 0, which is 1. So at this point, the slope is exactly 1. And so that's also a fascinating thing because, the sine function it's hard to define. I mean, geometrically, you can define this, but the slope at 0 is exactly this simple number 1. And that is a little surprise, maybe a huge surprise, if you think about this. All right, so these are two functions that are very closely connected to each other. Let's do a couple of examples before we go to part 2 of this, the second segment of the video lecture for section 3.5. All right, can you differentiate x squared sine of x? And the answer is yes, you should be able to. The derivative of the first times the second plus, you see what I'm talking about, by the way? When I say first, I mean this. And this is the second. The derivative of the first times the second plus the first times the derivative of the second. Or you can write derivative of the second times the first if you like. So it's the first times the derivative of the second, right? And there's not much more you can do. This is the answer to this question. Okay. All right, let's differentiate this quotient. -2 cosine of t all over t squared. So this is f of t. Of course, the independent variable doesn't matter. Since it doesn't matter, we call that dummy variable. It's a really rude implied way of calling variable, but we call this the dummy variable because it doesn't matter what you call it. Okay, all right. Anyway, the derivative of this function with respect to t is, the denominator is easy, right? It's t squared squared, so it's t to the fourth. And the top, the numerator, according to the quotient rule, is first the derivative of the top, which is -2 times the derivative of cosine. That's negative sine of t. So I'm going to write sine of t and make that -2 into positive. So what I have written so far, 2 sine of t is the derivative of the numerator, okay, times t squared. And just so I am not confused as to, is this sine of t times t squared, or is this sine of t times t squared? I want to make sure that I don't include this t squared in the argument for the sine function. So this is the first part, and then minus the numerator times the derivative of the denominator, right? So that's going to be 2t. Okay, so this calls for some reduction or simplification. The top is 2t squared sine of t, and the second part is plus 4t cosine of t. I think you can simplify a little more. The top can be, let's factor the 2t, and then you get t sine t plus 2 cosine t divided by t to the fourth. Maybe you can simplify one more time by eliminating one of those t's. 2 t sine of t plus 2 cosine of t. Okay. Now, this last simplification may not be so important, but again, when you see things like t and t fourth on the top and the bottom, you might as well simplify them just because it's easier to handle this expression than the other expressions. Okay, so apply what you know. You have your product rule, the quotient rule, the power rule, the extended power rule. Those things can be very useful. All right, now in the second part of section 3.5, we will do the rest. We have 4 more trigonometric functions, not the inverse functions, but the trig functions themselves. So we will differentiate those. And it doesn't take a lot of hard work, okay? In fact, they will be pretty straightforward. Even though they may look messy, the concept itself will not be too hard, okay? So let's go to part 2 after we finish this first part video, the first part of the video for section 3.5.